Hello, I am Savannah Brandon, and I will be looking at mass spectroscopy and analyzing 4 different graphs to show how you can determine from the information provided by these graphs, what your molecule that you have actually looks like and its structure. So this is my mass spec graph for my molecule C5H7NO3. And so the first thing that we find is the molar mass is 129. And if you look here at the N plus peak, it tells you what the molar mass is. So then my degrees of unsaturation is 3, so that means that my molecule is 3 pi bonds or double bonds or rings. And so my first fragment is at 15, which codes for a methyl group. My second fragment codes for a methyl group with a ketone. And also, it is my base peak, 43, which is my tallest peak on my mass spec graph. Then if we go down here to 59, it codes for an ester, which is actually in my molecule. So this fragment is really important. And so that's all that my mass spec codes for. So this is my IR graph. And so we're going to start in zone 1, which is this region right here. And this peak right here stands for a primary or secondary amine, because it's a nitrogen stretch right here, which makes sense because there's a nitrogen in my molecule. And so then the next region is zone 2, and there's nothing in this zone right here. So we're going to move on to zone 3, which is right here. And there's nothing in this zone either. So then we're going to move on to zone 4. And in this zone, there's a dip right here at 1783, which stands for a carbonyl. And in my molecule, it stands for an ester. And then this is the fingerprint region, and there's nothing really coding for anything in this area. And we don't see any peaks for an aromatic because my molecule, although it has some type of a ring, it's not technically an aromatic. And that is my IR graph. So this is my HNMR graph, and this is my molecule here. And so this 3 hydrogen peak is coding for these 3 hydrogens right here on the methyl group, and they have the lowest electronegativity, since this methyl group is like close together and isn't as shielded by all these other things going on in the ring and by these oxygens. And so these 2 hydrogen peaks, so the lesser electronegative hydrogen is this one, and then this one belongs to this one right here. And so these are in the ring, and there's an oxygen here. That's why this one's a little more shielded than that one, but they're pretty similar hydrogen regions, so that's why they're so close together. And so then the next hydrogen region, and these 2 also have pretty similar environments too, but they're just a little different. And all these 3 have the same hydrogen environment. And so then the next peak right here codes for this hydrogen right there, for that single hydrogen, which is shielded by the ring and by these oxygens, and that's why it's pushed so far over, and it's really electronegative. And then this hydrogen, sorry, I don't know what color to use. This hydrogen area right here is actually an exchange. It's not technically attached to a carbon, so that means it's coding for this one right here, this hydrogen attached to a nitrogen. And those are all the hydrogens in the molecule, and that's HNMR. So this is CNMR, and this is my molecule again. And so this carbon is the least electronegative because it's not deshielded by the ring or the oxygens, so it belongs to the least electronegative position on the CNMR. And so the next carbon is going to be at 44.8, and that belongs to this one right here. So this one is also a part of a ring, but it's not attached to any oxygens. So it's going to be less electronegative. And so then 72 is the next position. And that one is going to belong to this carbon, which is also a part of the ring and is attached to one oxygen. So it's going to be slightly more shifted downfield due to that oxygen pulling its electrons. And so then a really far shift down to 165 is going to bring you to this ketone right here. So this carbon is obviously electronegative because it's attached to the nitrogen and the oxygen, and it's part of a ring. So it's going to cause a really big downfield shift due to that electronegativity. And then the most electronegative carbon is right here, which is the ester attached to the ester group. And so that's deshielded by these two oxygens, which is going to make it shifted really far downfield. And that is my CNMR. Thank you for watching my video about mass spectroscopy, and I hope you learned how to identify molecules through this.